Every year, more than 11 million tons of watermelons leave fields across the planet. They travel by truck, by ship, and sometimes even by plane, crossing borders, climates, altitudes. Yet most of them break before arriving, not in halves, not visibly, but internally, silently. Beneath the rind, under the weight of their own water, millions of fruits develop microfractures that no one sees, until it's too late. Transporting watermelons is not just a matter of moving volume, it's a matter of pressure. Each fruit is, in essence, a hydraulic sphere, a natural pressure vessel. With over 90% water content and a rigid, elastic shell, the watermelon reacts like a living structure. Its internal pressure fluctuates with vibration, acceleration, and stacking angles. A slight tilt during transit, a curve taken too fast, or a trailer vibrating out of phase can be enough to trigger the first fracture. And once the crack begins to propagate through the rind, there's no turning back. From the outside, it still looks perfect, but the inside is collapsing. This is where agriculture and mechanical precision begin to overlap. Just as pneumatic seeders rely on airflow dynamics to distribute grains with millimetric accuracy, fruit logistics are beginning to discover that minor physical variables, pitch, angle, torsion, radically influence structural integrity. In a modern planter, seed trajectories are altered by air turbulence. In a truck bed, watermelon fractures are shaped by the pitch of the trailer floor. The analogy isn't poetic, it's physical. Heavy industry has known this for decades. In mining, for example, conveyor belts that transport fragile ores operate with strict vibration and curvature limits. The aim is simple: prevent cracking by controlling dynamic load, speed, arc, and material density are calibrated to avoid shock. It's a system designed to protect rocks, literal rocks. And yet, in the global transport of perishable fruit, we still rely on wooden pallets and flatbeds with no vibration logic, millions of dollars in losses, and still no adoption of the principles used in ore logistics. There's a metric that barely appears in standard inspections, but that tells the true story of what happens during transit: the radial compression index under dynamic load. It's more revealing than any external visual cue. It captures how the rind responds to internal hydraulic shifts when stacked, jolted, and compressed. The same kind of stress measured in structural fatigue tests in engineering labs. And yet, this data remains mostly ignored in fruit transport operations. Which raises a simple, yet uncomfortable question. If the mining industry calibrates vibration frequency by mineral density, why are we still shipping thousands of tons of fragile, water-loaded fruits on generic, non-adaptive pallets? It's not just a question of spoilage, it's a question of engineering logic, or the absence of it. In one of the most delicate food transport chains in the world, the watermelon isn't just a fruit, it's a test case for how much intelligence we're truly applying to the journey between field and fork. The journey begins with silence. Pallets loaded in the early morning, stacked with mathematical precision, each fruit wrapped in expectation. But the first fractures happen where no one sees. Between the warehouse and the ramp, in the seconds when a forklift shifts its weight, or when a container jerks forward on a slope. It's during these subtle transitions, often imperceptible, that stress begins to concentrate along the rind. A stress that, for watermelons, behaves like a silent fissure waiting to travel. At the microscopic level, the watermelon's rind isn't solid. It's a layered elastic barrier, rigid on the outside, fibrous inside, designed to handle internal pressure as long as that pressure remains stable. But during transport, nothing remains stable. Each vibration, each deceleration wave, each loading tilt exerts force in a direction that the fruit wasn't biologically designed to resist. The result is microcracks, invisible hairline failures that grow with every kilometer. And when the fruit arrives at its destination, it may still appear whole, but it's already spoiled from within. To solve this, engineering looked elsewhere, not to agriculture, but to aerospace. Polymeric mesh liners, originally designed to cradle foam core panels inside aircraft fuselages, have been adapted for fruit pallets. These liners don't just cushion, they diffuse impact by spreading shock over multiple nodes, a principle used in aeronautical insulation. Applied to watermelon transport, the effect is immediate. The impact that once concentrated on a single pressure point is now distributed across the entire crate, reducing fracture initiation. The numbers confirm what the rind had already been feeling. In comparative tests, shipments that used vibration-dampening liners experienced a 36% reduction in visible cracking, even though stacking methods remained exactly the same. No change in position, no change in crate volume, just a change in how motion was absorbed. A simple mechanical buffer transformed the outcome, not by eliminating vibration, but by respecting the physical limits of the fruit structure. This change isn't theoretical. In Brazil's interior, a large producer replaced traditional crates with biofoam cradle pallets, a solution inspired by reusable impact systems in high-value electronic shipping. The result? An 18% drop in fruit rejection within just one harvest cycle, less loss, less spoilage, and above all, less energy wasted, moving broken fruit through a system that never knew it was broken. But the real shift isn't in the crate, it's in the logic. For years, logistics teams have measured vibration at the base of the container, as if all fruit were equally rigid, equally shaped, equally reactive. But a watermelon is a curved structure, a dome under pressure. It doesn't crack based on overall shock alone. It cracks based on how that shock bends across its curvature, how pressure translates at rind level per kilogram of arc radius. The new challenge, then, isn't to remove all vibration. It's to model compression across fruit geometry, to understand each watermelon as a biomechanical object whose failure points can be predicted, even prevented, with the right physical insight. What breaks a watermelon isn't what we measure, it's what we ignore. The silent fracture that starts in motion and ends in loss. The cold chain is often seen as the safeguard of freshness. From harvest to market, the assumption is that colder equals better, a shield against spoilage, a delay button on ripening. But in the case of watermelons, the wrong cold can do more harm than good. Beneath the refrigerated promise lies a delicate thermal equation. The rind, the water inside, and the air outside form a balance that is easily disrupted. And when it is, the consequences are structural. Inside a refrigerated container, temperatures are tightly controlled. But what they rarely consider is the biological memory of the fruit. Watermelons evolve under sunlight, in fields that heat and cool across the day, where internal pressure shifts gradually. When cooling is too fast or too deep, the rind doesn't adapt. Its elastomers shrink before the internal fluids respond, forming vacuum pockets between cells. The result is a shell under tension, stiffened, brittle, primed for fracture as soon as ambient temperatures rise again. Instead of preserving the fruit, aggressive refrigeration sets up the conditions for failure. The rind loses elasticity, but the internal water remains in motion. The moment the container doors open and warm air hits the surface, internal pressure rebounds, and cracks begin to form, not from impact, but from internal stress cycling. The fruit breaks itself from the inside, under the force of its own stored imbalance. To address this, cold chain engineers began to rethink refrigeration, not as a static number, but as a curve, one that mirrors the field. By simulating diurnal thermal patterns, warm midday, slow cooling at dusk, controlled decline chilling protocols began to emerge. These systems delay internal shrinkage by pacing the drop in temperature over hours instead of minutes, allowing the fruit's internal structure to follow. The cold no longer shocks, it synchronizes. The insight came with data. In shipments cooled just 0.5 degrees Celsius below the dew point, rind fractures increased by 24% upon unloading, compared to those chilled in phased stages above the dew curve. It wasn't the temperature alone. It was the relationship between the cooling rate and the watermelon's internal tolerance. The most fragile point wasn't the coldest, it was the transition. In southern Spain, where watermelons are exported in peak summer, one logistics company implemented a dynamic chilling algorithm based on solar patterns from the growing fields. Instead of a fixed refrigeration target, containers adapted their cooling profiles hour by hour. Over the course of the season, crack-related rejections dropped by 29%. The fruit was not only colder, it was calmer, thermally speaking, less stressed, more resilient. The strategy is subtle, but transformative. Refrigeration should not be a number. It should be a narrative, a temperature arc that mirrors where the fruit came from. Instead of treating containers like freezers, we begin to treat them like simulated sunrises and sunsets. A system that cools by understanding the biology it carries. By recalibrating not for ambient air, but for rind tensile response, the cold chain becomes something more intelligent, more adapted, less destructive. Because in the end, overcooling doesn't just waste energy, it breaks what it was supposed to protect. Before we continue, here's something to think about. If protecting a watermelon requires this level of precision, imagine the detail behind everything else that moves through this invisible network. There's a reason we've pinned something special below. It speaks directly to those who understand the value of engineering, timing, and doing things right. Take a look at the pinned comment. It's worth your attention. The field has always been a space of precision. Modern seeders adjust their depth based on soil density, regulate force per square centimeter, and modify angle and speed in real time to ensure every grain reaches the ideal layer of earth. Every element is measured, every variation matters. It's this same philosophy, the logic of calibrated force, that needs to extend beyond planting into the unseen stretch that follows, the journey of the fruit. Transporting a watermelon is no longer a task of simple logistics. It is a problem of applied mechanics, a problem of stress vectors, of curvature physics, of thermal elasticity. The same way a planter senses when the soil shifts from clay to sand, logistics systems must begin to sense when the watermelon shifts from stability to fatigue, not by tracking boxes, but by understanding biology as engineering. In Japan, this redefinition is already underway. High-value fruit transport systems now use real-time stress sensors embedded in containers to detect changes in rind tension. These sensors communicate with onboard algorithms that predict crack probability zones before the damage occurs. Containers are then rerouted, recooled, or slowed down to reduce structural failure. Not just temperature sensors, not just GPS, but a live dialogue between the fruit and its transport environment. One that adjusts, reacts, protects. This approach reframes everything. It stops seeing the watermelon as a passive unit of volume. Instead, it becomes what it truly is, a pre-pressurized biomechanical cell with nonlinear fracture thresholds and time-dependent failure behavior. It's not how far the fruit travels that matters. It's how the journey applies pressure, where, and when, and whether the system carrying it can adapt to that. Just as agriculture once evolved from manual sowing to precision planting, the post-harvest phase must evolve from static logistics to dynamic structural management. Every fruit becomes a data point, every journey a calculation. Behind each watermelon, a choreography of mechanics and biology waiting to be understood. If a seeder can calibrate its force per seed depth, adjusting in milliseconds to the resistance of the soil, then the question is no longer whether fruit logistics can be precise. The question is, why haven't they been until now? Some things move quietly beneath the surface, shaping what we see, what we eat, how the world works. And sometimes, the most unexpected detail can change the way we understand it all. Curious minds don't stop at the obvious. If you've come this far, take a moment to check the pinned comment. You might find something there that speaks to your kind of curiosity,